Good evening, everyone, and thank you for joining. I'm Mayuri Hendricks, and I am a research technician from Kagan Lab. And today I will be talking about how lab management is essential. I'm just going to open my right slide, and there we go. When we think about the great discoveries and great scientific discoveries, we often think about the final results. The final results in scientific research is publication, the breakthroughs, the technologies, and the scientists behind it. But today, I want to focus on something which is very less visible, yet absolutely essential: laboratory management. This talk is not about paperwork and it's not about administration. It's about how and when lab management fails, what are the essentials which can help this lab grow? So let's begin with a simple question. What actually makes a great lab? If we ask what makes a great lab, the answer often comes quickly. Funding matters, equipment matters, talent matters, prestige matters. A well-funded lab can access technology, good equipment, collaboration, and expand its possibilities. Talent and people can drive creativity and discovery. But here is the important question. Are these enough? Can this make a great lab? Can funding alone make science reproducible? Can equipment alone create reliable data? The reality is that great laboratories are built on systems, not funding alone, not talent alone, and not prestige alone. Systems are what turn resources into reliable science. Systems create repeatability, and repeatability generates reliable data. Reliable data creates impact, and that's what we are looking as scientists. This shift, this is the shift I want us to make today from what we think about lab management as administration work to seeing it as a scientific strategy. I want to focus on what is the foundation of research and focus on this pyramid for 1 second. Most of people focus on the top of the pyramid: publications, funding, impact, and recognition. But every structure is only strong as its foundation. At the base is the lab management, where SOPs, protocols, people systems, and our day to day organization takes place. Above that are quality assurance, quality check, calibration, validation, and these supports reproducibility. Reproducibility supports reliable data, and reliable data is what creates impact and gives us our publications. Let's understand how science fails. Reproducibility crisis costs preclinical cancer research 28.2 billion each year. That's in dollars and that's in US. So imagine what is the impact in the global world. 1,500 scientists surveyed confirmed that selective reporting, pressure to publish, and different protocols are making gaps in repeatability. If a result cannot be repeated, it cannot be reliable. In 2016, Nature studies shows that 70% of the researchers are unable to reproduce other experiment results. 50% of researchers cannot even reproduce their own work. That is even more concerning. This is not a problem that individual scientists face. It is a systems problem. It tells us how documentation, design, data analysis, and standard operating protocols all matters. Now that we know that how science fails, let's understand when science fails and what happens when science fails. One of the most cited examples comes from a company called Amgen. They did a study in 2012 where they tried to replicate 53 of biomarkers. These were preclinical cancer studies, out of which only 6 could be reproduced. That number is uncomfortable, especially for anyone working in cancer. But the research and the lesson is that science is not broken. The lesson is that every step matters. hypothesis, experiment, analysis, validation, publication, and reproducibility. One break in a process can cause the whole system to fall. Let's have a look at what are the costs when science fails. When processes fail, we lose funding, we lose researcher time, and we lose public interest. And most important, in cancer, we lose lives. This is why lab management matters. And this is why lab management should not be a later activity. It protects scientific investment, it protects researcher efforts, it protects the credibility of results and the impact that we will have in future. So if the systems are the foundation, what are the essentials of the lab which we can follow in research? I want to frame that a great research lab work around six essentials of the great lab. So these are the six essentials: people, quality, reproducibility, safety, infrastructure, and continuous improvement. I personally think if we incorporate and focus on these essentials, we can make a great research lab. These are not separate boxes, these are all connected. Together, they create research excellence. Let's begin with the first three: people, quality, and reproducibility. First, people. People are the core of the lab. A great lab is not only a collection of instruments, it's a community of people who understand their roles, guides, and supports one another. Second, quality. Standard operating procedures, quality assurance, and quality control must be designed into the process from beginning so that your lab becomes great in documentation and traceability. Third, reproducibility. Good science should be repeatable. That means reliable methods, accurate records, digital notebooks should all be version controlled. When these three comes together, the lab becomes more productive. It becomes more trustworthy. But excellence also depends on how we manage risk. Let's have a look on how we manage risk. Fourth, safety. Safety is not separate from science. Science is scientific risk prediction. Risk assessments, cost, biosafety, protocols help us think ahead and prevent harm. Fifth, infrastructure. Equipment maintenance, calibration, and validation determine whether data can be trusted or not. If equipment cannot be trusted, data cannot be trusted. Continuous improvement. Continuous improvement and excellent laboratory works similarly together. In order to not avoid any mistakes, a personnel should be trained. That is where CAPA, corrective and preventative actions, which teaches the personnel what to do and how to do it, comes in view. I want to take you through some real examples from our Kagan lab back in Glasgow. It's a very sunny day today, so hello everyone again. So in our lab, there are three major things which we are doing at the moment: Drosophila and mammalian cell culture, and we are testing how drugs will enact on it. So in Drosophila research, one fly can change everything. A mislabeled stock, an incorrect genotype, or poor documentation can invalidate whole years of research. In mammalian cell culture, one contaminated flask can affect the entire project. Core facilities and shared infrastructure. We also share our equipments with the whole Wilson Wall Cancer Research in Glasgow, which helps us not only to have different research modalities, but also helps us to build collaborations. This is where students, ECR, and technical staff also comes in place. Laboratory management is also a form of scientific training. For students, it builds scientific habits early: SOP documentation, safety, attention to detail, focus. For PhD researchers, it supports project ownership, accountability, and reproducibility. For ECRs and technical staff, they often are the extension of the lab. They not only hold the knowledge, but also maintains systems which supports excellence across the project. So one can say that lab management system is also scientific leadership skills. And these skills even become more important as science enter the new era, which is the AI era. The future era coming AI boom will transform the research. But AI does not remove the need of good systems. Good systems plus AI can accelerate the discovery. But bad systems plus AI can accelerate a lot of errors. Unreliable data and AI can scale so many problems for all the research which has been done for ages. But it cannot replace the judgment, collaboration, curiosity, and mentorship of a personnel. And this is where personal scientific community and ethics and values comes in place. Now that we know what are the essentials of the lab, let's see how will the future of the lab look like in 2035 when the AI is incorporated. Imagine where Imagine a lab where digital systems are integrated, AI quality systems are already supported, reproducibility is monitored in real time, calibration is automated, equipment and maintenance is so predictive that you can lessen down your research time. The future is already here. We all are using AI, but the labs that lead tomorrow are the ones which are investing in it today. And strong labs do not only exist without lab management, but it also depends on what equipments we have and what resources are we using. As I come towards the end, I want to leave you with 5 practical questions to ask yourself to save years of research. Do your SOPs reflect what actually happens at the bench? Could someone reproduce your work from records alone? When did you last calibrate your critical equipment? Do your students know why they follow a protocol or just how? What processes will break if you leave tomorrow? I hope these questions, if your lab is essentials and are complete, are ready to answer. And my final message is great discoveries are remembered because they can change what we know, what we can treat, and what is possible. But behind every discovery is a system called lab management and collaboration. I want to acknowledge my amazing team, Kagan Laboratory from University of Glasgow, my professor Ross Kagan, Dr. Hamid Badmos, and all of my amazing team, the workshop, the Fly-NeuroCan community for having me for this talk. Thank you. And I'm looking forward for the questions.
Presentation. We'll take some comments and questions from the house, and then we can move to comments and questions online, and then even from the faculty. Comments. Line 1.
Yes.
Comment. Line
Thank
2.
you.
Comment and nominate somebody. Okay.
I'm just gonna close it to get back on.
Video. Okay.
Stop share. Yes, there we go. Yes. Hi. Hi, everyone.
Alfred. Okay. Okay. Faculty first then. While they think about their questions.
That's fine.
All right.
It's been a long day.
Yeah, quick question, Mayuri. Thank you so
Yes.
much for this. So,
Thank you.
what do you think is the most difficult part of the lab essentiality? So, so in terms of getting as a new PI, for example.
Yes. I think with time as it's changed, and I've worked with different laboratories before. So when I was working in Glasgow Tissue Research Facility, everything was digitalized and a lot of documentation was there. So when we started, I think documentation is the biggest problem because we are just like, why do we want to write it? Why do we want to write? What did we do wrong? We don't want to own up to it. That's one of the things which is a people value kind of thing, like you should have your work ethics and values. That's number one. And second thing, you should care about what you're doing. So I think the biggest thing is to have documentation control where people do not want to do documentation. But as I said in my presentation, if you did not record it, it never happened. So record every mistake and learn from every mistake.
Response. My other question is, for those who would be interested in working as lab technicians, do you have some advice for them?
Yes. So early career researchers and students, as we all think that science is something where we need to do the research. And as I've worked with Ross, I have realized after working with a lot of companies that do not miss on the science, but also make sure that you are doing all the lab management properly. In order to just grow into lab management, I think the first step is to know in your own lab that is your SOPs done. Are you making the SOPs? Are you making documentation control? Do you have stock list? How are you managing that? So if you're able to manage these little tasks, I think in future, I'm going to give a real life example actually, just because I'm thinking. So once, I think Yumi would relate on this. So once we were we were working with COVID, and um, we were working with like a standard protocol, and nothing can be tweaked, but somebody was noticing the process so nicely that how much time it takes for one plate to get read, for the whole process to get done. And just because of one, there were 800 scientists, by the way, in that building working. So just one person to think about how much time it's gonna take for the whole process to complete, how much time we should do this, change the entire process. And we were one of the number one companies who were delivering COVID results each and every day. So I'm quite happy with that. So one of the biggest example is you need to be attentive and you need to know how you're documenting every process and how you go forward with this. Just channel it, manage it, and act on it. That's what I would say.
Thank you so much. We have two questions here. So,
Yes.
for researchers who develop innovative protocols that improve accuracy, what are the
Yes.
practical steps and common challenges involved in patenting these protocols?
Um, the main thing is that we kind of take, so usually when we are doing any protocols, we try to take what the company is telling us, but that protocol might not be standardized for the cells you're using. So basic research is where you need to do your background study check that if your cells are going to survive in that same, like for example, we're working with some kind of cells, one particular kind of cells, which we're not going to name, but colorectal cancer cells, which doesn't adhere. And that was one of our SOPs written that we have to keep it for 5 minutes after trypsinization. And I and Hamid were looking into it, and we realized that it doesn't, like the cells do not float after trypsinization. The cells do not come off the adherence. So Hamid and I tweaked the SOP on the basis of the cell lines. We did some background research, and that's where you need to have that research gap and balance. And in order to have these research SOPs to be patented and to be your own work, you need, I'm not entirely sure, but there are SOPs which are written in research articles, which you can patent it, and you can have that standard protocols just because
Yeah.
somebody did it.
Yeah, and
Yes.
that leads to the next question. So
Yes.
this person is asking, how can laboratory managers ensure that intellectual property is protected before publication or dissemination?
I think records and documentation. So since the process even starts, we need to start with grant projects. We need to have timelines of what we're going to do and what will be the deadline. So divide the projects in small little parts with date and time, review those projects, also document everything online. Now, because paperwork is a lot of hassle and paperwork can just go, missing or something. I think shared notebooks like SharePoint is the biggest example where you can have shared Excel sheet which is shared to everybody and have that documentation right. So once you have all the, it's like thesis writing, if I would want to say for students in here. Once you start writing your thesis at the very end, you have lost the plot. You have lost what you started off with because there's so much data which you have forgotten and you don't know how to match that. So now, if you have documented it from the starting, I think you would have had something to work on.
Okay. So the last question, if you're managing a very large lab, you
Yes.
have equipment, you have, apart from just the fly, the reagents and everything, and how do you ensure, because I saw in your presentation that you put it there that you should check the equipment, service them when necessary and all of that. How do you ensure that this maintenance gets done at the right time, and then it's followed up? Maybe if they tell you they are coming back in 3 months, how do you ensure that there is proper maintenance of lab equipment and resources in the lab?
So, as I manage the lab, and Ross has been very kind, but Ross also has a lot of fly stocks. So he has more than 1,500 fly stocks. And we make sure as soon as the fly comes in, we have the genotype sticker and everything. The sample labeling is very important. Whenever you start any experiment or you get any sample, label it, because one fly can look similar to another fly and you don't know. And when you're in doubt, I would say to just erase it, and as Ross would say, to just bin it. So I would just stick to that. So now, once the sample comes in, my first process is to label it. Second process is to digitalize it. So as we have a shared notebook where we write what are stock listed, what is the genotype, when did it arrive, and how is the stock doing. After 3 months, me and Ross also goes back to the sheet if any fly stocks have died and what do we need to do. So that's another part of mitigation strategy and how to assess that. So that's one thing which we kind of do just to regulate and like have these practices, because you don't know what can happen tomorrow.
So,
Thank you so much, Mayuri. Just to add to
Thank
what
you.
you've just said. So regarding
Yes.
the equipment, so what we've got over there is that they're actually labeled. So
Yes.
basically we've got when to service them. So and the last
Yes.
service date as well, and when the next one is due. Exactly. So for
Yes.
every equipment we've got that. Is
So
that okay?
for
Yeah.
equipment calibration, we have yearly equipment calibration, and we also check it by ourselves within 3 months with water just to see if the 1 mil pipettes are working. Also, equipment, if equipment, like for example, we have a cellometer, and if the cell counts are coming different, we also try to check it manually in a traditional way. So always have that check and always have regular calibration of the equipment. And also, I would say weekly run a calibration on your equipment just to make sure that all the results are coming fine and the equipment doesn't have any faults.
Okay, yeah. So Prof will just talk to us about intellectual property shortly, and then I want us all to listen because we have a lot to learn
Thank
from
you.
that. Thank you. Welcome.
Thank you. Thank you so much. Thanks.
thank you, Mayuri. Yes, please. In impromptu, probably yes. Yeah. You all hear me? Yes. Okay, I know how to stop voice. Does this help in any way? Okay. Now it's become a formal speech. So, over the last couple of days, and it just came up again, is the concept of intellectual property. So, with your indulgence, I just want to take a couple of minutes to explain why you should care about it, what exactly is it, how it plays a role in your sort of day-to-day science. Okay? So, because I know some of you know a lot, some of you know very little, so let's just get on the same plane. And it's something, as a scientist, you're just going to have to know about it, full stop, right? So intellectual property, I think you understand that what we're talking about is protecting and patenting work that you do. So first of all, let me explain why you would want to do it, and then let me explain what it is, okay? And I think I can do all of that in like 2 minutes. The reason you want to patent what you do, let's say you discover a new gene that drives a tumor, or you discover you have a hit from a screen that you do for a lead compound. We're not a drug yet, but a compound. If you publish it before you protect it, then it will never see a patient. Let me just say that again. If you publish it or you give a talk on it, you announce it publicly before you patent it, it will never see a patient. Doesn't matter how much you really love humanity, it will never see a patient. Doesn't matter whether you care about making money at all, it will never see a patient. So for what we do, we want it to land on a patient. So things that are patentable get patented. Why is that? Because to run any typical clinical trial will cost millions, maybe tens of millions, sometimes even more dollars. Unless you have that in your pocket, you're going to have to work with pharmaceutical companies to push your drug, your ideas, and so on forward. The first question they're going to ask is, did you protect it? If the answer is no, they're going to ask you to please don't let the door hit you on the way out. Because if you don't own it, then they can't own it. It is public property. And so they could run the trial. They could spend $100 million to run a trial. But because you have announced it sneakily, which is why they check carefully, then any generic company can just make it after they're done running the trial and make all the money. Okay? So they have to own it if they're going to drop real money into it. And that means you have to own it if you're going to be able to work with them and give it to them. Does that make sense? Okay? So if you want to make big bucks and buy an island, or you want to give it all back to charity, that's on you, but you've got to protect it. That's the first thing. This is why this keeps coming up, and this is why Elfie, is that her name? Elfie? Aoife. That's why she was so frustrated by the state of getting her ideas patented. Okay? So that takes me to the second thing. So I think all you really need to know about patents is that it costs a little bit of money to do, but you can actually write the patent with AI these days. So it costs a little bit of money to file a patent. So let me explain. There's two types of patents you need to know about. There is a patent where I have an idea, or I have, for example, I have a new gene that causes this disease. I figured this out, right? So it's a knowledge patent. It's what's called a no, it's not a composition of matter. It's the exact opposite. It's blanking on it. It's a use patent. Okay, so a use patent is basically an idea. I have the right to use it. Now, a lot of times you will patent something as a use patent, not even so much to protect it, because maybe it's not, the idea is not so valuable, but you're keeping somebody else from patenting it and blocking you from working on it. All right? So that's a very common thing. Now, use patents aren't so valuable because let's say I have an idea for making, instead of a 96 well plate, a 95 well plate. Okay? And I patent this, it's a great idea, and I make a use patent of it. Well, somebody can get around it by making a 94 well plate, okay? So use patents are not considered super valuable. They're mostly you protecting yourself. So companies in particular, when they have something, they put a use patent on it so that nobody else can get that. Okay? Less useful, but it gives you what's called freedom to operate. The one that this guy said, that's the actual valuable one, is called a composition of matter patent. So use patent, composition of matter patent. Composition of matter patent is a thing that you made, a compound, usually, something like that, okay? A new device. All of these would be a composition of matter patent. It is a thing that you have made, you're protecting that thing. That's the thing that most companies and investors want to see, is do you have a composition of matter patent? Because now you own something, you know, I can make a 94, but you've already patented the 95. And also, the 94 is now going to be difficult to patent because there's something called obviousness. Once you make something, it's hard to say, well, I'm just going to tweak it a little bit. I'm going to paint it green instead of red and call it something that you can't do that. There are things called obviousness, but that can be done with a composition of matter patent, harder to do with a use patent. Does that make sense? Those are the patents. And then the final thing I'll add to that is patents are a two-step. So you file what's called a provisional patent. You have something, maybe you have a prototype of your 95 well plate, okay? That's a real basic one. Anyway, so you have a protocol. You would file what's called a provisional patent, and then that gives you a year to get it straightened out. Turns out 94 is better. So you spend a year, you test it out, you find out 94 is the way to go, and then when you file the full patent after a year, and you have 1 year file a full patent. It is, well, it was going to be 95, I tweaked it, now it's 94, and here is the full patent, okay? And those costs that you've heard about thousands of dollars and so on, that is usually the full patent. At least back in the day, a few $100s will get you a provisional patent. I don't know about Nigeria, but I suspect it's in that range, okay? So people have lots of provisional patents, and occasionally will convert it. Usually when you go to the full patent, that's when your university says, I do or don't want to pay for this, okay? And that's that moment where then if they don't pay for it, they give it back to you, and you can pay for it yourself if you have confidence in it. Does that make sense? Okay, that's pretty much what I would say. Is there any questions?
There's a question here.
Yeah.
So this person said, how then do we work with this kind of intellectual property and working in silos? When you keep that idea to yourself, waiting to be published, isn't that working in silos?
Yeah. So the question is, if you're not telling others about it, aren't you creating a silo? So first of all, not telling. So like I said, there's two types of patents: composition of matter and use. There's a third way, which is what's called a trademark, okay, which is basically you not telling people, okay? The answer to that question is, it is creating a silo for a moment, all right? And it would, in a perfect world where we all have wings and they're sparkly wings and we get to fly around, we would be able to tell each other everything all the time and still get things to patients, okay? But sadly, you leave childhood, you grow up to be an old man, and you have to deal with the world as it sits. And so what that means is there's a bit, and I think most of you don't go blabbing everything you know all the time anyway, so it's not that big a burden. You usually wait till you're at least close to publication before you just tell her, I did have an incident once early on, and this is why I'm now old man and not young man, where we put a big deal up, put a big finding that we had, a student of mine, on a poster at a meeting, and somebody did that and published it before we did, like a month later, okay? And that was a grow up moment for Ross, right? So, and the student wasn't super happy either. So real world, yes, and thank you for that question. There is a balance, and that is, hold it if you think it's going to be something that you want to bring to a patient, especially, and then when you're ready to publish, go and decide, is this patentable? And we can talk about, I don't want to dominate this session here. We can talk about how to get advice on whether something's patentable. Just because it's new and it's never been done before doesn't mean it's worth patenting. Okay, we can talk about that. That's a slightly different topic.
Yeah. Like, how much are we looking at when we talk about patents and trademarks?
Say again?
Like, how much, like how much cost involves in getting something to be trademarked, and then like if you invest that, like how much is coming out of it?
Yeah, so trademark we don't need to talk about. Nobody here is going to be trademarking anything. I could trademark Ross Kagan as a trademark, but you know, nobody's been fighting me to get this Ross Kagan name and slap it on everything. If they did, then God bless them. So let's talk about costs for patents. So to do a provisional, US, UK, all right? So if I'd known I was going to give this little spiel, I would have done the Nigeria one. So let's assume it's in that range. So to file a provisional by yourself, so you go to ChatGPT and say, I've got a 95 well plate. I need you to write me a patent because I'm not going to pay a lawyer $15,000. I have paid lawyers, okay, as this one knows, to write patents. I should say I've got 14 patents, okay? So if you want to do it yourself now, you have ChatGPT write it. They do like a really good job. It will cost you in the range of, depending on a few things, $500 to $1,000 to file it, a provisional, okay? So it's not nothing, okay? But it's not crazy, okay? To file the full one, there's two types you can get of a full patent: local, Nigeria, or global, all right? and they have very different cost schemes. So I would say real world to file a local one will be in the $10,000 to $15,000 range. Okay, so that's more than pocket change already, and that's annual. And then to do global will cost you another 20 to 40,000. Okay. Yep, and that's why you want to. Your institute has an opinion about whether they want to put money for it. Okay.
Yeah. Thank you.
We're good.
Yeah, we're good.
Okay.
Thank you so much.
Yeah.